Hello everyone. Let's work out some problems on the compression steel topic. So this problem is for HSS type of column. So the problem statement reads: an HSS 5 by 2.5 by quarter braced column is supported. As shown in this problem, determine the controlling slenderness ratio. So this is the same column. From the strong axis, it's free sway, and for the weak axis, it's prevented, right, with hinge. If you go to page, if you bear with me, let me find the page for you. If you go to page 454 and find the section given here, we're giving 5 by 2.5 by a quarter, and then pick up the Rx from it. So the first column represents the shape type. If you go across, you go to the x-axis, and you underneath it you find the R, and from the R you find the value, which is 1.73 inch. The LX is given already, which is a 20 feet here, assuming the strong axis is the x-axis. And then for K is 0.65. If you go to the K table from my previous lectures, you will find it's 0.65. Now, as far as the 0.9, as far as the RY for the same column, if you flip the page and go to page 456, you'll find also the same shape on the first column, and then the second section of columns, axis, y-axis, find the R, and you will find the R value, which is 0.99. The L here is 10, right? Because it's the column is has been braced from two sides, so it's 10 this time, not 20. And K is 80, again from the table. So then your slenderness ratio for X is KL over R. Plug and chug, it gives you 90.17. And for KL over R for Y-axis, plug and chug, it gives you 96.10. So the larger controls, and this is your solution. That's for the first problem of today's lecture. The second problem is problem 10.5, an unbraced frame of this figure here. Let me grab my laser pointer. Bend along the x-axis. Determine the effective length factor for AB and BC columns. So they want you to find K for this column, AB, and K for BC, not the entire system here. So we've done similar problem before when we divide the solution into column section and girder section and find G at each joint. So we'll find the G for this joint, and this joint. We don't have to find the values or any values for this column here because it's not needed. It's just AB and BC. So then for joint A, we have only one girder and one column. So the column is, they all W18 by 35 because it's just one column. So we have the W18 by 35. The moment of inertia for this column here, again, you go to, I believe, page 434, go to W-shape properties table, table C.1b, and you should find all the values. So you find the value here for the moment of inertia, which is 510 for this section. The L is 14, because that's what is given here. And then you divide this by this, it gives you this value. The same thing for the girder, right? Because it has a girder. And you find the value to it from the same table. Just you have to flip it through the pages to find the moment of inertia. And then your L here is a 25. You divide this by this, it gives you 11.64. Then if you divide this value by this value, it gives you 3.13, which is G value at A joint. Now, as far as the B joint, you have 2 girders and 2 columns. So for the column section, you need to list the 2 columns. You need to find their moment of inertia with their length. You divide this by this by this, then you add them up. You find 70.43. The same thing for the girders. You find 28.15. You divide this 70.43 over the 28.15 gives you 2.50. And that's your G value. For C joint, you have 2 girders and 2 columns. The same procedure is done here, and your G is 1.55. So then what you need to do is to go to the alignment chart, and for GA, because right, you're going to consider this is GA, this is GV, and cross them, you find K value, just like we did in the previous lecture, and your K value for this column is 1.8. Then you take GB and GC, so this is JA and JB in the alignment chart, you cross them, and your value is 1.6 for this K here. And that's it. That's what they ask you to find.